Good morning, physics fans. How we doing this fine sunny Monday morning? Yes, it is Monday morning. It's sort of tough keeping track of the days here, but it is Monday morning. Weatherman said it's going to be pretty nice outside today. Maybe get outside and get some fresh air, go walk along a path somewhere, do something nice. Hope you had a good weekend. Hope everybody's safe in your household. I hope everybody's illness free in your household. Continue to keep your social distancing. Continue to do our part, be able to get ourselves to a new normal and get ourselves back to some sort of normalcy here. Once again, continue to work on answering the questions at the end of the lessons. Gives me feedback in regards to the work that you've done. Every once in a while I'll put the wrong answer there, my bad. Caffeine is not the thing that keeps the body warm. It's caloric, so please do keep up with the material though. We have 2 more chapters to go through. We have heat and dealing with the heat and what we're dealing with right now. We'll start talking about melting things and what it takes to melt things or it takes to freeze things. And then we will talk about thermodynamics, the first, second law of thermodynamics, and that should complete it. So we have 2 more chapters to cover here, and we'll get through this as quickly as possible. So hopefully, once again, you're keeping up with the material that we've been dealing with. I've tried to keep it at a pace that we can handle. And once again, we'll just continue to work through this. Today we're going to talk about the idea of temperature. The idea of temperature. Once again, the kinetic theory of temperature, and this is what we talked about on Friday, is the temperature of an object is proportional to the average kinetic energy of the particles of the objects. So no matter what the object is, if it's really big or if it's really small, okay, they have the same temperature. This has more molecules, so the entire kinetic energy of this is more than the entire kinetic energy of this. But when we take the average of this, then that takes us back to the exact same temperature. So when we're talking about the average kinetic energy of the particles, that is proportional to the temperature of the object. A thermometer is a device that you place in contact with another object or in an environment to achieve thermal equilibrium. The thermometer. We put it in water to find the temperature of the water, or if you're feeling sick, you put it under your tongue, okay, and you achieve what is called thermal equilibrium. Okay, you achieve the exact same temperature, and that will be the thermal equilibrium, and that tells you what the temperature of the body is or whatever object you have. The liquid within the thermometer, what you have is you have a liquid here. Our liquid is blue. Okay, that liquid that's in there will either expand or it will contract. Okay, because you have what is called thermal expansion. When you heat something up, the liquid tends to expand. Okay, when you cool things down, you tend to shrink things down. Okay, so when you have warmer temperature, it's going to warm things up. Well, this fluid in here is going to expand. It's going to expand, which means it's going to raise up to a higher level here, which is going to be the temperature, or it's going to contract, which means it's going to go down. Okay, that's the same thing with respect to thermometers that are outside. The temperature will tell us to either expand or contract that fluid here. Okay, so within the thermometer, the temperature will or the liquid will either expand or contract. Okay, and that will give us a measure of our temperature. The thermometer is calibrated. It's calibrated to measure the temperature of object due to the amount of expansion or contraction of the liquid. So right now, if I would hold this thermometer in my hand, okay, it's going to rise up to 98.6 degrees or whatever Celsius is. Well, you can see the blue is going up, which means it's expanding because I'm warming things up. Because my body is warmer than the environment here. The environment here is about 70 degrees in here. my body is 98.6 degrees. So you can see the thermometer is expanding, or the fluid in the thermometer is expanding because I'm warming it up. Okay, I'm adding heat to this thermometer or the fluid that's in here. So I'm almost at 30.2 degrees or 32 degrees Celsius. And it's almost done. So that would be thermal equilibrium. Okay? That would be a thermal equilibrium that I'm achieving between the thermometer here and my body because I'm in contact. If I would take and remove my hand from this, well, what happened is it's going to contract because this is going to cool down, and this will go down to whatever the room temperature is. Thermometers are usually filled with mercury. They're usually filled with mercury, but that's a toxic, it can be toxic and poisonous to you. So if you break a thermometer, you have to be able to be very cautious in regards to contacting of the mercury. But they still use mercury to be able to fill thermometers. And some are filled with alcohol. They must be accurate. They're most accurate temperatures when they're between boiling and freezing. The newer thermometers, okay, are electronic sensors. Okay, back when I was old school, when I had to take my temperature, okay, they had a thermometer, it was a short one like this. They just stick underneath my tongue and figure out what my temperature was. Okay, now you have the electronic ones that you stick under your tongue, and in 5 seconds or 10 seconds it'll go beep, 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 and you achieve thermal equilibrium. You also have those sensors now that they put on a forehead to be able to measure your body temperature at that point. So there's all types of different technology that has improved thermometers and temperature reading. But the old school was they're filled with mercury, filled with alcohol. When you get outside the freezing and boiling range of water, when you get outside, the gas thermometers are more accurate, which means they're filled with hydrogen and they're filled with helium. So the gas thermometer is a little bit more accurate when you go outside the boiling and freezing point of water. And once again, if I'm going too fast, just hit the pause button here. Temperature scales are calibrated and are dependent upon the freezing and boiling points of water at sea level and in standard atmospheric pressure. So we don't have a high pressure or low pressure system. We have a standard atmospheric level or pressure. You're at sea level. You're at sea level, which means the pressure is more normal than if you're up at a high elevations where the pressure is not as great. So we have temperature scales are set and calibrated depending on the freezing and boiling points of water at sea level. When you have a degree, this is an increment. Maybe. This is a division or an increment on the thermometer. You have these little things here, little lines in here. Those are divisions, those are degrees. We have the Fahrenheit degree, which what we deal with because it's an English unit, and we don't want to convert over to metric units in the United States. So we have 32 degrees Fahrenheit and 212 degrees Fahrenheit. This is freezing, this is boiling. So you have 180 degrees between those two, and thermometers are calibrated for them. We have the Celsius scale. This is named after Andrew. Miss a W in there. Andrew Celsius, and sometimes called the centigrade. The centigrade scale. which takes us from 0 to 100 degrees. You have 100 degrees, which is once again a multiple of 10. Okay, is a multiple of 10, and once again the Celsius and centigrade or any type of metric units deals with those multiples of 10. They go from meters to, or centimeters to meter, meters are multiplied by 10 twice. Okay, so that is why it's also called a centigrade. When you talk about centi, that means 100. So you have 100 degrees that are there. We can convert from degrees Fahrenheit to degrees Celsius. Maybe. If I take 9/5 and multiply it by my Celsius degrees and add 32 to that, that will give me my Fahrenheit's degrees. If you rise 1 degree Celsius, that's a rise of 1.8 degrees Fahrenheit. Kinetic energy. Once again, going back to the kinetic theory. The kinetic theory. Kinetic energy of atom must be positive if a substance is kinetic energy of an atom must be positive if a substance has a negative temperature. Just because you have a negative temperature does not mean you have a negative kinetic energy. Kinetic energy is a scalar value. Average kinetic energy must be positive. Kinetic energy, once again, is a scalar value. It's just a value. Just because you have a negative temperature does not mean you have a negative kinetic energy. You still have kinetic energy there. Okay, you still have your kinetic energy there. You don't have a negative kinetic energy. We still have it's just a lesser amount. And once again, kinetic energy is proportional to what the temperature is. So your average kinetic energy, you still have a positive average kinetic energy, even if you have a negative temperature. Kinetic energy is a scalar quantity. William Thomson. Also known as Lord Kelvin. Lord Kelvin. He discovered the temperature scale, the Kelvin temperature scale. Okay, he was the inventor of the Kelvin temperature scale, and we use Kelvin a lot when we go into when we get into our heat transfer that we will be dealing with later. Next couple of days, we'll be dealing with heat transfer. We'll be dealing with Kelvin temperature. When you're over in chemistry class with Ms. T, you dealt with Kelvin temperature also. When dealing with your boils, your ideal gas law, and so on and so forth. There exists no upper limit to temperature. We don't have an upper limit of temperature. There exists no upper limit. The sun's core is 1.5 times 10 to the 7th degrees Celsius. Whew. That's pretty high. That's pretty high. Even other stars can get hotter than that. Okay, so other stars are even hotter than the 1.5 times 10 to the 7th Celsius. So there's no upper limit to a temperature, but there exists a lower limit. There exists a lower limit to a temperature. Once again, if I'm going too fast, push your pause button and catch yourself up. When a subatomic matter, when all subatomic matter stops moving, there is no kinetic energy. If you have no kinetic energy, that's 0 Kelvin. That's absolute 0 temperature. Okay, when you have no kinetic energy, now you have 0 temperature because you have no kinetic energy. And kinetic energy is proportional to the temperature. This is called absolute 0. And this occurs at negative 273.15 degrees Celsius. negative 273.15. That would be cold. Degrees Celsius. This is 0 Kelvin. Now, if you know when you deal with Kelvin, we have no degree symbol there. It's just Kelvin. It's assumed to be a degree temperature. So you have just 0 Kelvin. Also, as gas cools, so think about this. As the gas cools, once again, you have very little movement. You have lesser and lesser movement. They contract and reduce in volume. If the gas can remain a gas at 0 degrees Celsius, then the gas will reduce down to a 0 volume. So if you have a gas and you can remain a gas, because once you take a gas and you start to cool it down, it's going to form a liquid form. You take the idea of heat, water vapor. Water vapor cools down, it will turn into a liquid. Okay, it will turn into a liquid. And then if you cool it down more, it will turn into a solid. Okay, so you have your 3 phases that you go through, a gas, a liquid, and a solid. Okay, so you have those. If you can keep a gas, and reduce it down to 0 Kelvin, the molecules of the gas will stop moving, and the volume would reduce down to 0. If you think about helium, helium liquefies at negative 268.8 degrees Celsius, which is 4.35 Kelvin. So helium can almost make it there. Helium can almost make it down to there, but it can't quite make it there. Now, how they sort of alter those things is they increase the pressure, and they can turn, because you're looking at PV is equal to PV, or PV equals nRT. If I increase my pressure here, I can increase my temperature, just dealing with your ideal gas law. So if you can pressurize the helium, you can turn it into a liquid by pressurizing the helium. But just in a normal atmospheric pressure that we have here, it would take us to go down to negative 268.8 degrees Celsius, which is 435 degree Kelvin, or 4.35 Kelvin. Now, how do we convert Celsius to Kelvin? We just take our Celsius degree and add 273.1315 degrees. So we take our Celsius degrees and add 273.15, and we get our Kelvin degrees. And the Kelvin increments are also equal to the Celsius increments. So if I change 1 degree of Celsius, I also change 1 degree of Kelvin. So if I increase 1 degree Celsius, I increase 1 degree Kelvin, because 1 degree Celsius equals 1 degree Kelvin. It's the same increment. Okay, so we don't have to adjust anything in that regards to be able to change the idea of Celsius degrees Celsius. We'll be talking about this also. We'll be talking about this also when we start talking about what occurs when we go through phase changes from water to gas, or from solid to a liquid. We'll talk about our temperature change, and we'll be utilizing this idea here. It doesn't matter if it's Celsius or Kelvin, it's going to be the same degree change that we have there. This goes into the idea of temperature and the working with the ideas of temperatures and the 3 scales that we have. We'll be dealing with mainly Celsius and Kelvin in here. Tomorrow we'll start working with the idea of going through phase changes, solid to liquid, liquid to gas, what it requires to be able, how much heat it requires to be able to change those phases. Once again, I'm looking to try to push ourselves through the last 2 chapters of our physics here. One deals with the idea of the heat and and what it takes to be able to change phases, and then we go into some thermodynamics, and that should complete the school year for us. Please complete, I gave you 5 or 6 problems, please complete those. Please complete those at the end of the notes. Once again, please do keep up with the notes. Once again, everything's going well for you. If you have any questions, feel free to contact me at any time. Send me a message through Google Classroom, and I will help out as much as possible. Other than that, I'm out here. Adios. We'll see you tomorrow. Miss you guys.